All right, so hopefully you have a good understanding of how to name ion compounds from formula units without transition metals. Now we're going to expand that technique with transition metals. There's a little bit more detail we need with the transition metals, but it's the same basic process of naming. Naming the metal first, full name, or the cation first, full name, and then we are going to name the anion with either an "ide" or the polyatomic ion name, right? But for the transition metals, we have to add one more step because we have to tell you what the oxidation state is of the transition metal. Remember, I've always told you that the transition metals can have multiple oxidation states. Well, we need to understand what the oxidation state of that metal is when we write the name. So this tutorial is going to do that. This tutorial also is broken up into two different sections. So if you understand how to get the oxidation state of a transition metal from a formula, you can skip over to the point where it just talks about how to name it after that. So that's about slide 7, right? About halfway into it, right? But we're going to go through both of these right now, and then at the end, everything will come together. Okay, so as I mentioned, transition metals sometimes have multiple valence. And why is this? Well, some of the transition metals are able to use electrons in the d orbital as valence electrons. Now, I've always told you that the valence electrons are the s and p, and that is correct. But in some cases, remember when I told you that the 4s and the 3d are very close in energy, sometimes there's a rearrangement of the electrons in the orbitals to achieve the lowest stable state. And to do that, sometimes the d electrons are moved around a little bit, right? And the s, right? So we can use some of the d electrons as valence electrons in specific cases, right? But not all transition metals have multiple oxidation states. Zinc is one of the ones that doesn't, and so is scandium, right? I'm not really worried about that right now, that you know all the ones that do and don't, but just be aware that not all the transition metals have different oxidation states. Here's one thing that you do have to remember is that the alkali and the alkali earth metals, group 1 and group 2, will never have multiple oxidation numbers, right? So if you see calcium or lithium, magnesium, sodium, they're always going to be their proper oxidation number. So if it's a group 1, an alkali metal, it'll always be +1. If it's group 2, it'll always be +2. It'll never be +1 or +2, right? Always +1 for alkali metals, always +2. And one more thing here, the chemical formula, or the formula unit, is actually going to tell you what your oxidation number is based on the structure in that formula unit. And I'll explain that in the next couple of slides. Okay, before we get too far down on how to get the oxidation numbers from the formula, let's just talk about some of the more common elements that have multiple oxidation numbers that you will see in class. So one of the most common ones is iron, right? Iron and copper are the ones that we have most common with in class. So there's iron 3, which is a +3 oxidation state, and iron 2, which is a +2 oxidation state. Here's iron 3, iron 2. Both are iron, both behave the same, but now we have +3 as an oxidation state and +2. Copper 1 and copper 2. We have chromium. Chromium actually has multiple ones. We've only given you 2 here. There's chromium 2 and chromium 6. There's actually chromium 4, chromium 3. Vanadium 5 is +5, and vanadium 2 is +2. Lead is another one, has 2 and 4, and tin is another one, 2 and 4. Right? There's other ones. There's silver and a couple of other ones that we may see. But for the most part, these are the ones that we'll see a lot of in class. Okay, and now we're going to figure out how do we assign these oxidation numbers based on our formula. Okay, so determining the oxidation number in a transition element in a formula is fairly straightforward. And you have to remember this really important and basic concept. The total overall charge of our cations in our molecule or our compound has to equal the total overall charge of our anions, right? So all the pluses, the total number of pluses has to equal the total number of minuses, all right? Now, if you get that concept, finding the oxidation number of a transition metal is very straightforward. So let's see how it works. So you're going to look at your compound formula, and you're going to say, how many of the transition metal elements are there in my formula unit? Do I have 1? Do I have 2? Do I have 3, 4, etc., etc.? Then the other important thing is you have to look what it is bonded to, or what they are bonded to. So what is the anion the transition element is bonded to, right? And then the two questions you have to ask on that is, how many of the anions exist, and what is the oxidation number of that anion, right? So the anions are not going to have multiple oxidation numbers, so there's no guesswork here. Oxygen is always going to be -2, nitrogen is always going to be -3, chlorine, bromine, iodine, fluorine are always going to be -1, sulfur is going to be -2, etc., etc. Based on their position on the periodic table is going to tell you the oxidation number, right? So you should know that nitrogen, phosphorus, for example, are always going to be -3, sulfur, oxygen, -2, all the halogens -1, right? And then you do know the oxidation number or the charge on the polyatomic ions because you have a list that you can consult during a quiz or a test that gives you the oxidation number of that particular polyatomic ion, okay? So then it's very straightforward. The oxidation number of your transition metal, remember this is the key equation here, is the number of anions in the formula times their oxidation number, which gives you the overall number of negative charges in your formula, divided by the number of atoms of your transition element, gives you the number of that gives you the oxidation number. And I'm going to show you how this works in a few seconds, right? So charge times number must equal charge times number, okay? Because of this. So let's see how this works. Okay, so the first step is let's assign the oxidation number for all the transition metals listed in these three compounds, okay? Or these four compounds, I'm sorry. And then we will worry about naming them in a later step. So let's just first understand what is the transition metals oxidation number. So let's look at our first compound here, TiCl4, right? Now, we know that the element, the transition element is titanium. And we can see that titanium is bonded to 4 chlorines, right there, 4 chlorines. And we know that chlorine is always -1. So we can say that there are 4 chlorines times -1 for each equals -4. So that's the total charge of all the negatives in my compound here. Now we need to have the equal number of positive charges. So we need to have +4 on the other side. Okay? And we're going to divide this number here by the number of atoms of the transition element in our compound. So how many do we have? We only have 1. So in this case, the oxidation number of titanium is going to be 4 plus, or +4. Okay? Because 1 titanium times +4 equals +4, and 4 times -1 equals -4. When you add the -4 to the +4, you get 0, and the overall charge in the compound has to be neutral, which is 0. Okay? So let's look at the next one. Here's my next ionic compound, iron oxide. So let's look at this one here. We always know that here's my iron. That is my transition element, and it is bonded to oxygen. So we know that the oxygen is always going to be -2, and there's only one of them. So we have one oxygen times -2 equals -2. And so we need a +2 on the other side to make it neutral, and we only have one iron, so that means that the iron has a +2 oxidation number. Because we have 1 times +2 must equal 1 times -2 as far as the charges, right? I know it doesn't work out mathematically. 1 times -2 doesn't equal 1 times +2. But remember, when we add the charges up here, they have to equal 0. Okay? Now let's look at another form of iron oxide, right? This one here. Now, same basic principle. How many irons do we have? We have 2 irons in this case, and we have 3 oxygens. So again, starting from the anion count, right? We have 3 anions, 3 oxygens. So we're going to write 3 times, we all know that 3 oxygens, times -2, so we need -6. So on the other side, we need a +6 total, right? And now we look back at our iron, and we see we have 2 of them there. So each one must bring in a +3. Now why do we know that, right? 2 times +3 gives me +6. 3 times -2 gives me -6. -6 plus +6 must equal 0, right? So basically the number times the charge has to equal of the cation has to equal the number times the charge of the anion, right? Last one here, real quick. Let's look at this one here. Now you should be able to follow this along real quick with me. We have copper. That is going to be my cation, and we have 3 of them. And we look at our anion, and that's PO4. That is what? That is phosphate. And phosphate is a -3 charge. You can look it up on your polyatomic ion sheet. So we have 2 times -3 for the phosphate, that's the PO4, equals -6. Now it's telling me here that I need +6 from the other side, and to get that +6, I have 3 atoms that are contributing to it of the copper, so we divide by 3, and we get the copper is +2. Okay, so now we have all the oxidation numbers of the elements here. We know what they all are based on the formula. Now we can use this information to help us write the proper name for the compound. Okay, so before we move on and start naming, you're going to have to do some practice on getting the proper transition metal oxidation state. So you're going to assign the oxidation number to the transition metal in each one of these formulas. Now, you're going to need your periodic table or your chart with your polyatomic ions for some of these to look them up, right? I'm not giving them here. So you're going to need it for nitrate and phosphate, right? Everything else here, the other anions, are all part of the periodic table. You should know those by now. Right. So your goal is to assign all the oxidation numbers for the cation, which are all the transition metals here. So if you followed any of my videos, you're going to stop the video, copy the information down, work through the problems, and then start the video when you're ready to get the answers. So when you're ready, stop the video now. Okay, I'm not going to go through all the information here, but you can see here that these are the proper answers for the questions, right? Remember, we did this example already, right? -2 for oxygen, so therefore iron has to be +2. And I give you a little bit of a reason here just to help you get through it. But hopefully you've got all these answers down. If you missed one or two, I wouldn't worry about it too much, but you should make sure you understand how the concept works. So if you got the methodology for determining the oxidation number of your transition metal in your ionic compound, you're almost all the way there for writing the actual name of the compound, right? There's only one more additional step that we do that we haven't done yet with the other naming of ionic compounds, and that is to include some information about what is the oxidation state of your particular transition element in that compound. So we've already got the first step done. We determined the oxidation number. Now what we're going to do is the same thing as we did before. We're going to write the full name of the transition element. So if it's iron, we'll just write iron. If it's copper, we write copper, right? Then we're going to follow that with a parentheses and a Roman numeral that indicates the oxidation state of that transition element in that compound, right? Remember, it's very specific to the compound. We showed you two examples of iron oxide. One is Fe2O3, the other one is FeO. Both are iron oxide, but both have different oxidation states of the iron, right? So we need to tell you which one you're using in the word version of the chemical formula, because otherwise you're not going to know. If I just write iron oxide, you don't know if I'm talking about iron 2 oxide or iron 3 oxide, okay? Fe2O3 or FeO. So the iron 2 means that the iron atom has a +2 oxidation state, all right? So the Roman numeral is the oxidation state of the transition metal in that particular compound. Okay, now we don't write +2. Some of you might ask, why don't we just write the +2 as the oxidation state? It's just not done that way, right? So vanadium with the brackets of V means that the vanadium has a oxidation state of +5. Okay, and then you just write the name of the anion as you would for any other ionic compound. So for example, V2O5 is named as vanadium 5 because there's, remember, you can figure that out here, oxide. Iron chloride is named as iron 2 chloride because the iron is in the +2 oxidation state in that particular compound. Okay, so there you go. That's pretty much it. So let's get some practice on it. Okay, so let's name the first one. So you have to do a bunch of steps here, but I'm going to do them all with you right now. So first thing we need to do is determine whether or not, what is our oxidation state of our cation, which is our copper, right? So we know we have 3 of those. We know that PO4 is -3, so let's just write here, right above here, we have -3, and we only have 1 of them, right? And so each copper must have +1. So the copper is the +1 because, again, we have 3 of those times +1. When we add it to -3, that gives us 0, right? The PO4 is -3 by itself. All right, so now how we would write that? Well, we write copper, and then we write Roman numeral capital I, and then we just write phosphate. Right? And that's it. You're done. Tells me exactly what I need to know. Copper is in the +1 state, phosphate. So when I form this compound, I know that I'm going to do it like this, just as we would do the crisscross method. I would just put Cu +1, PO4 -3, cross them, and then you get the actual compound that we came up with. Okay, so that's why it means, that's how you get that. That is the importance of putting the oxidation number for this. Phosphate is always going to be -3, so you don't have to tell that. Let's look at the next one. All right, we always know that nitrogen is going to be -3 for our oxidation number, so we can just put that right above it, -3. And since we only want to have 1 iron atom in the molecule, or compound, then we have to assume that since there's only one, it's got to be plus 3, because plus 3 plus minus 3 gives me 0 again, right? So it has to be neutral. So again, we would just write this as iron, brackets, parentheses, Roman numeral 3, and then nitride. Again, if you were to write this, it's Fe3 plus Ne3 minus. You do the crisscross, right? We get Fe3 N3, but we can reduce that to Fen. And that's where it is. So again, that's why we need to write the oxidation number for the iron, right? And the last one is, let's do the last one real quick together. I'm not going to worry about the crisscross for this one, but I know that tin has to be plus 4 because I have 4 bromines and each one is minus 1. So this is minus 1. This has to be plus 4. Right, so it's tin 4. So we would write tin, then the Roman numeral 4, bromide. And it's not any more difficult than that, right? So remember, you got to write the thing that a lot of students make a problem with is they write the Roman numerals at the end of the problem, at the end of the name, or they write a Roman numeral for bromide too. They don't. You only need it for the cation, and you only need it if it's a transition metal. And you only need it for a transition metal that has multiple oxidation numbers, right? But for your case, for moving forward, since you don't know which ones are which, just write the oxidation number in brackets for every transition element, okay? Okay, so we've come to the second to last slide in the video, and this is the one that you're going to do your practice on. So you need your periodic table out to help you, and you also need your polyatomic ion sheet to help you with that. So, and again, you're going to basically figure out what the proper oxidation state is for the transition metal in the compound, write the proper name for that in the text, and then put the proper name of the anion at the end. So when you are ready, stop the video and then start the video when you want the answers. So stop the video now. Okay, so hopefully you've gotten all these answers correctly, and if you made a mistake on 1 or 2, that's still pretty good, right? Again, a lot of these things are you're going to see multiple times in the thing. Now, there was a tricky one at the end here, manganese 7, right? So if you did this one here, you got 14, and you divide by 2, and you got 7. And there is a manganese 7 oxide, right? But the ones you're going to see a lot of are, again, copper sulfate, iron sulfide, lead oxide, copper oxide, etc., etc., right? So as long as you get the principle down of making sure that you write the charge or the oxidation number for your transition element as a form like this, lead, Roman numeral 2, iron, Roman numeral 3, then you're well on your way to understanding how to do this. If you're still struggling with this after watching this video and doing the stuff we in class, you should get together with me one-on-one so I can work with this with you on a more intimate basis. All right, so we can get you through this. All right. Because if you don't understand this, you're going to be using the wrong compounds when we do other things in the science, okay? So, again, if you got it, great, and if not, make sure you find me and so we can work through this together.